So now we covered the buck boost, and the boost. So we covered all our three converters. What I'd like to do next is I'd like to show you a lot simpler method for you to be able to go through all these equations just by sight. I mean, because if we go through a half bridge and a flyback, I mean, you have a lot of resistance. You have the resistance of the winding of the secondary, the primary resistors, the bridge RDS ons. We want to also include switching losses, maybe diode losses if we're dealing with synchronous rectifiers. I want to look at the switching losses. And if we do it this way, it's going to be pretty cumbersome. It's going to be a lot. It could be done, and step by step we can do it. But there's a better way. As I was playing with these equations, I noticed that, the power loss is just equal to an average current times a voltage source, if there's a voltage drop that's fixed. And that's going to be the power loss. And if it's any resistor, it's going to be the RMS squared times the resistance. And that's going to be the power loss. So all I have to do then is to look for these different losses, whether they're resistance loss, then I multiply by the RMS current squared. If they are a loss due to a voltage drop, like a diode, can be broken up into a physical diode voltage, forward bias of the diode, plus a series diode, a series resistance of the diode. And that will be broken down into I average times the V diode. Okay, so it's either going to be an RMS squared times an R, or an I average times a voltage. And, why is that? What you have really is one power. The power is defined as 1 over T integral 0 to T of V of T I of T squared. This is it. This is the power that we need. That's it. So what does this mean? This means if I have an input voltage, that's V sub G, and I have a current running through it, that's an I sub T, what do we have here? Well, if this voltage is fixed, what's the power? Well, use the same equation, 1 over T, integral 0 to T of, well, what is V of T? Well, V of T is VG. That's your VT. There's no time. This is a DC voltage. What is I of T? Well, that's just I of T. I don't know what the current is. DT. But look what happens. Because V of G is constant, I pull that out of the integral. 1 over T, integral from 0 to T of I of T dt. What is that value? This, by definition, is I average, is the average current. So this means power being dissipated in the or supplied for V sub G is going to be the voltage, the ZC voltage, times the average current. So whatever the waveform looks like, if the waveform looks like this during that time on, and it looks like DTS, well, guess what? Then it goes to 0, and let's say that's the current. Well, I just look at the average current and pop the average current in here. And then the power supplied by the source would be V sub G times DI, which would be the average value that I see. Okay? What if is not a sourcing, but it's supplying through a diode D? Well, at some point that diode is biased here. So we can consider the diode current and some fixed diode drop. So we can imagine that is like a voltage source drop, which is VD. And then later we'll add in the series resistance, the resistance of the diode. So now this is what? What's the power dissipated in the diode? Again, the same equation. You go back to here. So, but again, what happens is what's V of T? V of T is fixed. It's a fixed voltage, fixed by the diode current. If you're supplying 20 amps, then you look at 20 amps and you find the in the spec what the forward drop is. Okay? So again, I could pull that out of the integral. I got VUD, then it'll be times 1 over T, integral 0 to T of I of T dt. Whatever the waveform looks like, if the waveform kind of looks like goes to 0 and it only occurs during d prime t and it goes to I like we did many times, then this is again the average current. So that one part of the power dissipated in the diode is Vd times I average, and I average of this waveform is d prime times I. Okay? Now, if we add in and we say, hey, I have a diode resistance and this block as well. I can convert those two. Fine. I can still find the power dissipated. I still have I of T. Don't say I. It's I of T flowing through there. But this we already know. So this power dissipation, of course, the whole device now, this device, which is the diode, this is the internal resistance, is going to be the VD times the I average, okay, plus this portion now. Okay, go to the formula. 1 over T integral 0 to T of what is, I have to find V of T and I of T. But what is V of T across the diode? V of T across that, the resistor. What is V of T across the resistor? Well, that's nothing more than I of T times RD, which is, of course, equal to V of T. So now I could substitute that back in. So the power dissipated in the whole diode is going to be the two terms. The DC term plus, now this is 1 over T, integral 0 to T of what? V of T is now I of T times R, RD, the diode, the resistance voltage across the diode, times what? We still have this I of T. Oh, wow, and of course dt. So let's carry one more. VD, I average, plus, well, this is a constant. So I could put RD out, and what is this? This is 1 over T, 0 to T. Look at this. This is IT squared dt. By definition, this is IRMS squared. That's by definition. Somebody came along and said, hey, I want to define this as IRMS squared. Okay? So, therefore, we have the power dissipated in the diode is equal to VD times the average current plus RD times the RMS squared. That's my total power dissipation in any of the devices. So, in other words, all we have to do is give me the wave shapes. What's the average current? What's the RMS current of all wave shapes that you'll ever see in switchers? And I put it in a table form. So from that form, all I have to do is knock off, hey, what does the waveform look like? Even discontinuous, I don't really care. Continuous, discontinuous, just show me the waveform. I can calculate the RMS, and I can calculate the average. And then I put it into here, and I find the power dissipated through any of the devices, whether it's a FET, whether it's a diode, a Zener diode, whatever it is, a BJT, whatever the device is. you give me the waveform, and I will then calculate the loss. So then we go back to what's the efficiency? Power out over the power in, or power out plus power loss. This is divide again by PO, power out, and this is the power loss over the power out. So what I mean by that is give me all the power losses. That's what I just did above. What are they? Just give me the total switching losses, RDS on, the diode losses, any loss. You just give me them. I plug that back in here. I got my efficiency. So again, let's go back and do an example of the buck converter with the parasitics and see if we get the same equation as we got using the figures here. Okay? So, there's my D. Again, I knew this before. This is the RDS on, the direction of the polarities. I'm going to put the Xena, diode, I keep calling it Xena. It's a diode. And the resistance, the resistance of the diode. I'm going to put the inductor and the winding resistance of the inductor. And I'm going to put your ESR and the capacitor. And I'm going to put here a resistor. So I already established what the polarity was. And this is all plus minus, the current I flows into the inductor, that's the inductor current. Again, what flows through here? That's the average current here. That flows through here. Now, that's different from the average current that flows through there. So I know the current flows through here. Okay? So all I need to look for is what are the waveforms. If I stuck a current probe here, what would that waveform look like? It would look like this. Again, I'm not going to use the slopes because you'll see it won't matter. When I use the slopes, I do the slopes in there, and you'll see that there's a little bit of a residual on there that we'll have to take care of. But not a problem. We can still use the same method. Okay? This is DT. And the current that's going to flow through there when the switch is on is going to be the I. Okay, what does this current look like? That current looks like up, down, again I, but during D prime T. And what does this current look like? What that current look like is going to be the total. It has to be equal to this plus this, which means a straight line to I, and that's why I flows there. Okay? So we know what the waveforms are here, and we know then what is this? What is the waveform going into the ESR? Where the waveform is the delta I. We're hoping that the whole delta I goes into the capacitor. So that's going to go into the ESR. And we know what current flows into there. That's the average current. That's V over R, and that's I average. Okay, so all we need to find is what is the power loss. The power loss is going to be equal to the what? Let's call this current here. Remember, we're going to have the average and the RMS of this waveform. We're going to have, we'll call this 1, and we'll call this 2, and we'll call this current in the diode here 3, and we'll call, we can call this current, yeah, that's 2. Okay, so everything is there, and we can call this RMS current if we want to find the current in here. In this, we can find the current waveform, and here is the ripple current. Okay, so what do we have? We're going to have R, M, S, because it's a resistor, 1 squared times what? RDS on. That's the current going through here. Plus, what is the current here? RMS of the second circuit squared times RW. Plus, I'm going to have the current here now is split between, I'm going to have an RDS on here, an RMS current here, 3 squared times RD. Okay. Plus, I have this loss. And that's going to be, again, the diode times I average of that 3. This circuit right there. Okay, what else am I going to have? Well, I didn't consider the ESR before in our other circuit, so I won't consider it this time, but I can calculate it with this because it's easy. But this is the ones I want to compare what we had before when we derived it during our regular volt-second balance. Okay, so now all we have to find out is what is the RMS1, what is the RMS2, what is the RMS3, what is the average value of the current that flows here, not the RMS. So we want the current in leg 3, in this 3, the RMS and the average. So what is that? By definition, you just go by definition. What is the RMS current 1 squared equal to? It's 1 over T, integral 0 to T, of I of T1, the current that goes on for that time on, squared dt. And what does that current look like? I said during that RDS on switch, it's on here, back down, and it sees the diode current during dt. Okay, so we want the RMS current of this waveform. Okay, and that's what it is. So when you calculate the RMS current of that waveform, RMS1 squared, you're going to find that it's going to be equal to D times I squared. Okay, that's the RMS current. Now, when we look at the RMS current in the second branch, which is, I'm going to redraw the schematic so that everyone could see that easier because I like to point to it. Remember, this was branch 1, and this was branch 2, 3, and this was branch 2. Okay. Okay. So we found the IRMS1 squared, and then we look at this one, and the current here is pretty much the I. Of course, we know what it's really going to look like. It's going to look like something like this. It's not a problem with I being in the center. It's going to be ripple plus, it's going to be the ripple plus the average current. And that's going to be up here. And the average is going to flow here, and the ripple is going to flow here. Okay? That's what we have. ESR. Okay. So, therefore, what is the power dissipation here for the RMS squared? Well, for the RMS squared, that's like a DC current that's flowing through here. Basically, the RMS current squared of 2 is just going to be I squared. So therefore, that power dissipation is going to be easy to figure out. How about RMS3 squared? That's going to be a waveform that looks like this. And that's going to be I during D prime T. And the RMS current of this is going to be, when you calculate it, just with the basic equation, it's going to be D prime I squared. Okay? And what is the I average of, what do we want? We want the I average of 3. The I average of 3 is simply going to be D prime I. Okay? Because D prime, the current flows there during D prime. Okay, so now my loss. Plug and chug. The power loss now, you go back to the equation and you got RMS, right? You have the RMS of the RDS on, which was RMS squared, which is DI squared RDS on. The second one was RW, that's I squared RW. The third one was this loss, the RD, and that's I prime I squared RD, plus the average value, D times I times the diode voltage. Those are the parameters that we have. What is the power out? Isn't that I squared R? As I said, this average current flows here. The ripple will flow here. Okay? So therefore, that's it. So what do I have here? I have efficiency is equal to 1 over 1 plus the power loss. Isn't this the power loss? This is the power loss over, and that's the power loss, over power out. Now we can plug and chug. This is 1 over 1 plus the individual ones. I could pull out an I squared here. But gotta be careful. There's an I squared here, so we have to bring that separate. So I could pull this out as I squared times D RDS on plus RW plus D prime RD. Okay, that's the squared, plus D prime IVD divided by, that's the power loss. That's this, power loss, divided by power out, I squared. You see how the I squares go out now? That's how we get it. The only component, weird component, is we have is this one now. Okay? We have to do something about that. But so far, we have everything in here. That's the efficiency is going to be equal to, but we have something here. We need to look at what this last term is here. Okay, so let's rewrite this. 1 over 1 plus. Now the I squares go out here, and it's just D RDS on plus RW plus D prime RD over R plus this term. That's D prime VD over IR. We got rid of one of the I's here to here. So we just want this to this. Okay? From here and here. Okay? So we need to evaluate that. Okay. So we know that I times R is going to be the output voltage. But that's equal to, right, D, the whole thing we're working on, V sub G times efficiency. In other words, the output over the input is D times the efficiency. That's the whole thing. Well, great. Then I could substitute an I for this last term. I can say that I now is going to equal to V sub G D efficiency divided by R. Okay? And then I could put that back into the equation for the efficiency here. And this becomes the efficiency is 1 over the stuff that we had before. This is D RDS on plus RW plus D prime RD over R. Plus, substituting that I becomes D prime V sub G over D and V sub G. That's VD and V sub G. That's where those terms come from. What do we have to do? We have an efficiency here. We have efficiency here. We multiply both sides by the bottom term and solve and extract the efficiency out. When you do that, and again, in my book, I do all the steps, but you can multiply and divide out, and you will get that the efficiency will be equal to 1 minus D prime over D V sub G over V, Vd over V sub G. And you'll get 1 over 1 plus d RDS on plus RW plus d prime RD over R. This is the exact equation that we solved before. So this method now is a very, very powerful method to just plug and chug, because all I need to look for is the waveforms. So what I did in my book, and I'll give you them here fairly quickly, is lay out every single possible waveform that I have ever seen in converters. Okay, so starting with the currents. Now remember, the I average is going to be defined as 1 over t by triangles is defined 0 to t I of t dt. And I RMS squared is defined as 1 over t integral 0 to t of I of squared dt. And those are the equations that you use to derive from a waveform to get the average and the RMS of that waveform. So these are the common waveforms. Okay, and I'm going to give you the RMS and the I average. Okay. So when we look at this, of course, the first one is an easy one. It's just a DC, and if this is the current I and goes 0, then it's this is I of t. Okay. And the RMS squared is the average. There is no, it's the same. RMS is I squared. And the average, of course, is just I. Okay, so that's your first waveform. The second would be, what if we dealing with a square wave here like this? And this is 0 current. And that's I of t. And that's I again. And this is during dt. This is during d prime t. Okay, when you substitute this and solve with this equation, you get the RMS squared as being di squared. And the average value you get is going to be equal to d times I. So that's the average and RMS. Now we'll do another common one and we'll keep going. The other common one is, notice this is during the on time, during the off time. What if it's equal to something like that? There's the current during d prime t. Again, the height of that I'm going to say is I. That's 0 amps to begin with, and this is I of t. The RMS current, I RMS squared, is going to be equal to d prime I squared. And the I average of this value is going to be equal to d prime I. Okay? Now we come into our typical ones that we see, and we're going to do all the typical ones. This is the inductor current, and this includes the ripple. You know, try to get a constant ripple. With this middle term being I, and the ripple here, peak to peak, that I call delta I. Okay? And this is the I of t. Now, the RMS current of this waveform is derived in my appendix, and the RMS current here is actually equal to I squared 1 plus 1 over 12 delta I over I squared. And that's the RMS. The I average waveform of this is I again. Okay? Again, these are derived in my appendix in the book. I'm just giving you all the waveforms. Next, what if we have another common waveform is we have a current, a sinusoidal current. It's another one that I see. And again, the RMS, if this is I peak here, okay, and of course this is minus I peak, symmetrical, okay, and that's T waveform, and that's I of T. And that's 0 amps in the middle. And what we have here is going to be IRMS squared, and it's going to be I peak squared over 2. And as we know, an average current in a sine wave there, says this is equal to that, the average current is 0. Okay. The next common waveform that we see is going to be, now we deal with the regular waveforms that we see that we see with this ramp coming up, the inductor ramp. Okay? And that's during DT, and we see that in the buck converters. And then it repeats. And so on. But this is the period T again. Again, I use T sub S as T, the same T sub S as T, so I'll just stick to T since that's what I've been doing. Okay, this is the average. Now I'm going to say right in here is that I, and remember the I is the inductor current. Okay, and this is ultimately still the delta I. Okay, so when we do this, again, when we calculate it, we'll find the RMS current squared is equal to D I squared times this nice little thing of 1 over 12 delta I over I squared. Now, this term here, you'll see when I derive it comes out. Now, what is this? You know, this term, if you're looking at this, a lot of times you can ignore this term. And therefore, then it would just become DI squared, like we found before. Even if delta I were fairly large, like let's say delta I were half the DC current, but this then would be 1/2 squared, which would be 1/4 times 12, which would be 1 over 48. Well, 1 over 48 compared to 1 is pretty small. So even if delta I were equal to I in the magnitude, this would still be 1 over 12, still be less than 10% error. Okay, just wanted to make that note. And then, of course, the I average is going to be equal to, again, D times I. Okay, the next one you'll see, of course, on those the boost and the buck boost during the diode current. And what are you going to see? You're going to see, remember I said don't worry about that I didn't include the ramp. Now I'm going to include the ramp. This is the ramp coming down, and this is during D prime T times. And again, what is this? Remember, that is the inductor current, which is always that way. Okay? And this is I of T. Like I said, that's I of T here. So we come back and find again, you know, after a while you get to know that that's going to be D prime. I squared 1 plus 1 over 12 delta I over I squared. Okay, and then I average is going to be equal to D prime I. Okay, what other ones do we see? Well, let's get into discontinuous conduction mode. What we're going to see here is in the discontinuous conduction mode, we're going to see a current of I of T on some waveforms. They're going to look like up, down, stop, and repeat. Okay? And this here is going to be I peak. Okay? And this here is going to be the time again, dt. But this time is going to be a different. We're going to label that d2t. And of course, this is always t repeating. So what I have when I derive this is the RMS current squared is d plus d2 over 3 times I peak squared. And the I average is going to be equal to D plus D2 over 2 I peak. Okay? Then the next is going to be, again, discontinuous conduction, but the waveform looks like coming up and down and repeats. And this is going to be I of t during the dt. And then RMS squared is d over 3, I peak squared. And of course this is the I peak. Okay, and then the I average is going to be d over 2 times I peak. And the last part here, another waveform that I see is going to be one that comes here to here. That's going to be into the diode that you'll see in the boost and the buck boost and discontinuous conduction mode. And that's I of t, and this is d prime. This is going to be d2 time d2t time. Okay, and then again I peak. And the IRMS squared is d over 3, and that's the d2. That's the d2 over 3 times I peak squared, and the I average is going to be d2 over 2 I peak. Okay, so the last one is the ripple, like I said, going from 0 amp in the center, going up and down, and that usually goes into the ESR cap. So all we have to do there is go ahead and find the RMS squared, and that's going to be equal to delta I squared over 12, kind of get where the 12 is coming from. And I average, of course, is equal to 0 because it's up and below, and these two cancel out into here and here. And so those are all the waveforms that I see. So the cool thing is, if we're in, say, a converter on a buck converter, and we know this is the RDS on, and this is the inductor, and this is RW, we know how, and even the ESR, we know that the waveform in here is this waveform right here, the delta. So we can calculate the power dissipated here from this equation right there. Bingo, we're done. We got that one. What is the power dissipated here? Well, if we go here, we need to go back to what the waveform looks like. And even if we're on discontinuous conduction mode, the beauty is I can do discontinuous conduction mode, not a problem. What does it look like discontinuous? It looks like up, down, flat. That's one of the waveforms that we had previously. And that waveform was back into this figure right there. Up, down, flat. And there's the RMS current of that waveform. So we come back into the circuit and we stick that RMS squared into here to solve for the power dissipation here. Now, what would be the power dissipation here? That waveform, remember, would start at 0 for discontinuous, come up, and drop. Well, where is this? Well, this waveform is right here. So we use this RMS, this current RMS times the RDS on there to find out the dissipation here. What do we use here? Well, we know this waveform is up and down this way. Wonderful. We know what this looks like. That waveform is here, and then this is the dissipation that we use here for D2 for the RMS. What did we use here for the average? We use this same waveform, and there's my average value. See? So now we have that power dissipation here. So now we have the power dissipation here, we have it here, we have it here, we have it here, and we have it here. So that's all the power losses. Over the power out is the efficiency. This method is a very, very simple to get any complicated system. All you need to know is what are the waveforms. Once you know the waveforms, I can apply this to Fourier converters, half bridge, push-pull, Weinberg, Chuk, Venable, Bartow converters. I don't care. Give me the waveform, tell me if it's resistors or fixed voltages, and I will give you the dissipation in any complicated system. Just requires a little practice and the waveforms. And that's it. Thank you.